Hey everyone, welcome to our last workshop of the day. So today we have Gilbert from Macro DAO presenting on EVM basics. So hopefully this is going to help you when writing smart contracts for the hackathon. And yeah, feel free to take it away, Gilbert.
All right. Hello, everyone. This talk is called EVM Basics. Pretty similar to a different talk I've given, but they're all different in very cool and important ways. So the point of this talk is going to be learning some EVM opcode stuff. This stuff it can sound scary, it can seem scary, but it's not really that bad. And even though you're not going to become an EVM opcode expert at the end of this lecture, what you should do is understand some basic stuff like which opcodes cost roughly how much amount of gas. And that'll help you in general, just build more efficient contracts. EVM opcodes are also important we'll get into that. But anyways, we're going to look at EVM opcodes, talk a little bit about what virtual machines are so that we can understand what the EVM is. We're going to look at how the EVM runs because it's just basically a stack and some memory. We're going to look at a tiny little syntax and then show how Solidity compiles certain code into certain opcodes. And then after that, if we have time, which I'm sure we will, we're going to do a little exercise in writing some contracts in plain old EVM opcodes, which is not as bad as it sounds. All right, so the main reason you want to learn this stuff is to become a better Solidity engineer. You want to know why Solidity is designed the way it is. Solidity is not a general purpose language. It is written specifically for the EVM. And because of that, it has a lot of strange looking design decisions. But if you understand the EVM, then it no longer looks strange to you. A lot of design patterns rely on low-level opcodes, such as contract upgradability, proxy patterns, and other things. You should know how the EVM works so that you have an understanding of how function calls work. That's very important for writing not just efficient code, but also secure code when you're doing advanced things such as DAO proposal systems or cross-chain bridges or things like that. And this last one is pretty much what anyone should be able to get out of this lecture, which is you should be able to easily do some gas optimizations for low-hanging fruit when you're writing Solidity. So let's begin. Virtual machines are named after physical machines such as your CPU, your x86, Intel, maybe your ARM, CPU. These are all physical machines, real life machines. And these machines, the way they work is that you feed them instructions. And those instructions each have what's called an opcode. And that's what we see here. So in order for your machine to run anything, any sort of lowest level instruction is going to require an opcode. Whenever you hear the phrase, computers are just zeros and ones, this is what they're talking about. These opcodes are all in binary. So like here is the binary value for the add opcode. Here's the binary value for the sub opcode. These opcodes are telling the CPU what exactly to do for whatever algorithm or whatever you are working with. So virtual machines are basically the same concept, except instead of hardware, now they're software. That's where the name virtual comes in. It's not an actual machine. It's not a computer. It's not a chip, but it's software that behaves like a machine. And the reason we say it behaves like a machine is because it also takes opcodes or binary code for running its programs. And the EVM is no different. The EVM is a virtual machine, not a physical machine. And the whole point of a virtual machine is so that you can write multiple programming languages that compile to the same bytecode. But the benefit is that the virtual machine will run not on just one type of hardware, but many types of hardware. So the EVM has this specification where it runs this binary, and then other people go and implement their own versions of the EVM to run on different platforms, which is great for decentralization. You don't want the EVM to be specific to Windows or be specific to a certain Linux distribution. That wouldn't be good. Instead, you want it to run on all sorts of hardware so that you have better decentralization. So that's the point of virtual machines. Now we're going to be looking at these opcodes here because these opcodes are the lowest level of instruction for any type of machine, physical or virtual machines. So just to put some obvious context into this, Solidity, when you compile Solidity, you're compiling to these opcodes. So let's see how these opcodes work. We are focusing on how the EVM executes these opcodes. So first, let's take a look at an opcode. So each opcode is 1 byte. 1 byte is 8 bits here. And that enables up to, I think, 256 opcodes, if I'm not miscounting there. But in any case, this is what the machine says. This is what the machine sees. This is what Solidity compiles down to, a bunch of hex bytes. But over here, this is the human readable name. So whenever we talk about the add opcode, we are just going to write out add rather than try to memorize the numbers here. Although if you work with this a lot, you probably have some memorized anyway. So on the right, we have a bunch of opcodes, and these opcodes are the human readable name. Now, some opcodes take arguments. Those arguments are either going to be the next binary in the stack, or sorry, the next binary in the code, or it's going to be the stack. So let's talk about the stack. The EVM is stack-based, which means that all opcodes operates off of a singular stack for its execution environment. In other words, whenever you run a function on a contract with a transaction, that contract, when it's running, it's going to get its own fresh empty stack. And it's going to run a bunch of bytecode. And all of those opcodes are going to be adding and removing from the stack. And that's how it does everything. So everything that Solidity can do, it's because of this little stack here. And also memory and storage, which we're going to get to later. But it's a very simple data structure. We don't get like hash maps. We don't get linked lists or anything like that. Everything is on a stack and some memory and storage, which is also very simple. But what we're going to do here is we are going to see how these opcodes execute in a nice visual manner. So let's first do push 1 is an opcode that takes the next byte and pushes it onto the stack. So here it takes the value 03 in hex and pushes it onto the stack. So now we have that to work with. Push 2 is very similar, except it takes the next 2 bytes in the bytecode and treats it as a value. So we end up with 4. Now, to be clear, each value on the stack is going to be a full 32 bytes. That is how the EVM works. Its word size is 32 bytes, but I am omitting a bunch of zeros here. There should be, I think, 63 zeros if I wanted to be explicit for each of these numbers. 63 zeros and then a 3, 63 zeros and then a 4, but I don't want to do that. So I just write the simple version. Push 1, 9, we push that onto the stack. Next, we have a swap 2. This is just to show you how you might want to manipulate your stack. Swap 2 will take the top item and then 1, 2 and swap them. So this will swap 3 and 9, as you can see. And add is an opcode that takes 2 arguments from the stack. So that means add will take 4 and 3. It will pop them off the stack. It'll add them together and then put the result onto the stack. So first it's going to take 4 and 3. It'll do its calculation and then put the result onto the stack, which is just 7. And this is generally how opcodes work. You're putting things on the stack, you're taking them off, you're doing calculations, and you can do most of Solidity using this model. Now, when we're talking about the EVM, we do have EVM specific opcodes. Caller is an opcode that doesn't take any arguments and just puts on message.sender in Solidity onto the stack. So when you call this, you get a new value on the stack, which is going to be the address of whoever is sending that transaction or whoever is calling that function. So EVM has quite a lot of opcodes, and all of those put together will allow you to do everything you can do in Solidity. So that's the stack. So yeah, each item is 32 bytes, regardless of what I write here. Every item is always going to be 32 bytes for those inclined on the details. So that's the stack. Now we can talk a little bit about memory. Memory is basically a infinite array, or sorry, not an array. It's better to think of it as a string. Think of it as a string of data. Here I have it split up, but these are not slots. These are just a better way of writing it down. Really, this could just be one long giant string that goes on forever and ever, but I wrote it like this to make it easier to read. Now, this infinite string, of course, in practice, it's not infinite. The more memory you use, the more gas it costs. So eventually you're going to reach an upper limit because you're going to run out of gas. But when you're working with memory, you don't have to think about how much memory you have. You don't have to say, allocate me 64 bytes and then use it like you might in C or C++. Instead, you just use memory. And if you have not allocated that much, the EVM will automatically allocate it for you. So you don't have to, there's no allocation opcode is my main point. So we just use it. So let's see how we store a value into memory. So first we have a push 1. We're going to push 3 onto the stack. We're going to push another value onto the stack. And now we're going to store the value 3 into memory. And specifically, we had to tell the EVM where we want to put it in memory. So that's what this OX10 is. This is telling the EVM, I want to put a value into this spot in memory. So starting here. This could be any value. You could put OX99. You could put a very giant, large number, but you probably don't want to, because if you put a really big number, that means you're allocating all of that memory and you'll probably run out of gas. But here I'm just saying, starting from this position, starting from this 0 right here, that's where I want to write the value 3. And don't forget, the value 3 is 32 bytes. So when we do store this, that consumes those arguments off the stack. Let me do that again. It's going to consume this. It's going to see this as the memory address. It's going to see this as the value we're writing. And then starting from here, it's going to write 32 bytes, which is all of those zeros plus 3. So that's how you write something into memory. To read something from memory, it's very similar. mload is the other side of the coin to mstore. And mload only takes one argument, which is why we push 10 onto the stack. And this is what mload is doing, is we are saying we want to read 32 bytes starting from the memory address 0x10. So starting from this 0, we're going to read 32 bytes, which is going to be the entirety of this purple text. So we consume that, and then all of this gets copied onto the stack. And now we can do that as many times as we want. We can mload this same address over and over again, and it's pretty cheap. Memory is cheap. So we've gone over stack, we've gone over memory. Storage now. Storage is very similar to memory. It's not the same thing. Storage actually has slots. Memory is like a giant string, but storage is more like a key value pair. So if we replace our mstore and mload with sstore and sload, S for storage, of course, we get pretty much the same result, but it's a whole lot more expensive. sstore here, whatever you do in sstore, you are using anywhere from 2,900 gas to over 20,000 gas. That's a lot of gas. Whenever your function call requires a lot of gas, it's going to be mainly due to S stores and S loads. Whereas when we were doing the memory only costs about 3 gas per operation. So that's a huge difference. And so only use storage when you need to, clearly. So again, storage is like a key value database. So here 10, instead of 10 being the memory address, now it's the key that you are storing into. And 3 is going to be the value. Values can only be 32 bytes. You can't store more than 32 bytes. If you have something larger than 32 bytes, then you need to split it across multiple storage slots. And that gets more expensive. Strings and arrays use that technique. Okay, so the main points to get out of this is opcodes operate on the stack, memory, and storage. Memory is like a giant string. Storage is like a key value database. Now let's look at a slightly easier way to read opcodes, and then we're going to tie this to Solidity. So we're just going to look at S expressions here, maybe labels as well. But yeah, so here is the code that we saw previously with trim. Trim is a tiny language that I wrote. If you use trim, that means if you use a parentheses here, then now you are inside of S expression land, which means you can write your opcodes like function calls. Here, mstore takes 2 arguments here. So this is a little easier to read than having to figure out what's going on over here. Same thing over here. So very simple syntax transformation. All right, that's it for trim. Let's look at Solidity opcodes. So with Solidity, we have basic stuff like message.sender, message.value. Now here it looks like we're accessing some object or something, or some hash map, whatever. But we're not. These actually, each line gets not optimized. It gets compiled down to a single byte each, or a single opcode each. Message.sender gets compiled down to the caller opcode. Message.value gets compiled down to the call value opcode, and so on. There's more, but these are probably the most common ones. So even though you're writing out a bunch of characters, you're actually only adding 1 byte to the final bytecode size of your contract. And in terms of gas, these are extremely cheap. Color, call value, each of these are only going to cost 2 gas to run each. So don't be afraid to use message.sender. It'll probably cost more gas if you set this to a variable than if you just write out message.sender. So that's pretty straightforward. Payable was a fun one because all functions that don't have payable are actually cheaper. All functions that do have payable are cheaper, my bad. So here's a function that does not have payable. And these are some opcodes that Solidity generates, rough estimate. Basically what it's doing is it is ensuring that the call value, which is, we saw that in the previous slide, message.value. So it is checking if message.value is equal to 0. It's ensuring that it's equal to 0. And if it's not equal to 0, then it's going to jump to somewhere in the bytecode where it's going to revert. So this bytecode is generated for each non-payable function, external non-payable function that you write. And in reverse, if you do have payable on a function, then this is not generated and your function is actually smaller in size. All right, stores variables. So here's probably the most important one, not important one, but here's the most practical one in the whole talk. So with stores variables, as you're probably familiar, they get compacted when they are small enough. Before learning how compaction works, we need to learn how the stores keys work in Solidity. So first of all, when you declare any stores variable, simple declarations do not actually generate any bytecode. So you can declare as many variables as you want. and that does not increase the size of your contract code. Now, when you actually use variables, that's when these declarations come into play. Y, let me go here. Y equals 7, that gets compiled down to an S store. The value 7 is here. And here's the key. Remember that storage is a key value database. So the key is here, and this is the value. The key here is 1 because of the way Solidity works. Each variable that you define, Solidity internally assigns its own storage key, and it does it by index. So according to Solidity, X has the key 0, Y has the key 1, Z has the key 2, and that'll just keep going and going for all of your Solidity variables, for all your contract variables. So that's why here, Solidity is storing 7 into the key 1. And here, Z is assigned to 2. It's because of the order of your storage variables. Now, this order makes not much of a difference if you're just deploying a simple contract. But if you're deploying a upgradable contract, that's when it really matters, because when you upgrade a contract, you do not want to reorder your variables, because then all of these will get messed up and you'll be storing and reading from this wrong key. But yeah, so again, Y is assigned the key 1. So that's why sload 1 is happening here. mstore and return, anytime, this is a general concept. Anytime you want to return a value, you need to return it from memory. So this mstore is going to be storing Y into memory somewhere, and then return will return from that position in memory. That part's not so important. Not yet. So yeah, these are all index-based. So depending on the order of your definitions here. Again, if you reorder these, like I'm going to swap Y and Z, then you will see that these numbers also swap. I think you get the idea. Okay, so here's the compact stuff. So compacting storage variables is probably one of the simplest ways to save a lot of gas in some of your contracts. So let's see and understand why. So a storage key value, the key is 32 bytes or 256 bits. The value is also 32 bytes / 256 bits. That's why if you define variables that are fewer than 256 bits, Solidity will compile code to store them in the same storage slot rather than 2 separate storage slots. We will see shortly how much gas that saves. But as you can see here, X and Y are uint 8. 8 is much smaller than 256. So when you put them next to each other like this, they are going to go into the same storage slot, which is storage slot 0. Let's see how that affects the opcodes that get generated when you use X and Y. So here, this looks a little more complicated, but it's actually not bad. First, we want to load X, and then we're going to load Y, and then we're going to add them together. Now, when we load X, we have an S load. We are S loading from storage slot 0, because again, both of these are 0. And we can't just load from 0 and use that as the value. The reason we can't do that is because that value now has both X and Y in the same storage slot. So in order to extract X from this value, we have to do some bit masking. And bit masking is a pretty cool low-level binary technique. It's not complicated, but it's fun. You can search that online later. But the short version is that it extracts certain bits from a value. So here we use bit masking to extract the last byte from this sload value. And that's what we treat as X. Here, Y is very similar. We load the entire value, which contains both X and Y. And here we bit mask the second to last byte from that value. And because this is the second to last byte, we need to shift it over so that it becomes its true value and not the stored value. Once both of these are on the stack, then we just do add, and that will take both of them off stack and add them together. But the main point to get out of this is not really the opcodes. The main point is that the S loads it uses greatly contributes to the gas cost of your function. If so, a cold S load is loading from a storage slot that you have not loaded from before. A hot S load or a warm S load is loading from a storage slot that you have loaded from before. So in this case, we load from 0 and then we load from 0 again. This means that, well, given this is the first function call, the first S load 0 costs 2100 gas, and then the second S load 0 costs 100 gas. So what this means is by loading from the first storage slot for both variables, we have saved 2000 gas, which is a pretty good amount of gas. This is only by using each one once. If we reference these variables more than once, then we save even more gas. In contrast, if these were in separate storage slots, then S load 0 would cost 2100 gas. S load 1 would cost 2100 gas as well. So that's why Solidity does this compaction. Even though it needs to generate more opcodes, these opcodes are way cheaper than 2000 gas. Maybe they cost maybe 6, 10 gas at most. So you're saving a whole lot of gas by doing this compaction for your storage variables. So this is the main thing to get out of the lecture. You want to compact when you can. Compaction also happens in structs. So if you have a struct, try to order your variables in such a way that they are together so that they use fewer storage slots. However, there is one small caveat to storage compaction. Storage compaction can be not worth it if you never use these variables in the same function call. So for example, let's say foo returned x, and then there's another function bar that returned y, or used it in some way. If x and y are never used in the same function call, then you'll never get the gas savings. Not never, but generally. You won't get your gas savings because in one function call, x costs 2100 gas. Later on, in some other function call, y costs 2100 gas. So you don't really get the gas savings here. So when you are trying to compact your variables, try to put the ones together that are going to be used together in the same function calls. Oh, I see something in the chat. If you apply NFT in that, how are the key saves? NFT IDs are inside of a mapping. Mappings are a little bit more complicated for how Solidity compiles it, but effectively it does a K hash of the mapping key. And that becomes the storage key. I don't think we'll get to that in this lecture. Okay, so quickly, here's an if statement. This looks a lot more complicated, but it's not. These are labels in trim. This is a trim specific thing, not EVM, but it makes writing code a lot easier. Basically, this just represents a spot, a position in your bytecode. So here, when we say jump to else, this is just going to jump to here. It's much better because you don't have to manually count how many bytes offset this position is in your code. That will be terrible. But effectively, here is the opcode version of an if else. Here we are checking if x is equal to 3. We sload x to get its value. We use the EQ opcode to compare it with 3. And if they're equal, then it jumps to here. If they're not equal, it'll continue and then jump to here. So this is not that bad. You can study that later if you like. One interesting thing to note is that, at least for now, Solidity will, I won't say that, it doesn't matter. Function calls, external function calls use the call opcode. There's actually 3 opcodes. There's call, there is delegate call, and there is static call. They're all external function calls, but they all work slightly different. But effectively, when you make any sort of external function call, you're using the call opcode. And when that happens, that function or that contract gets called, which means it gets its own stack, its own memory, and its own storage. Internal function calls are a little different. They are jumping to your own bytecode rather than another contract bytecode. We don't have to go over that though. Okay. So let's see. That's it for the slides. Now, for those interested, we have some small exercises here if you want to better understand how the EVM works. What I have here is some boilerplate. And then here is where you want to write your code. So this is a REPL that I built. It uses trim, as you can see. And it's just a nice way of playing around with opcodes and seeing how they work. This involves contract creation, which is why we have this boilerplate. This boilerplate will take your code that you write down here and basically deploy it to a contract address. That is what's happening in this first transaction. In this second transaction here, this is calling your new contract with some arguments. Usually you're not going to have to worry about this for now, but just to show you, let's do a push 1 4. And let me increase my window size. So down here, you can see there is a 4 on the stack. So if I push 4 and I push 7, here's what my stack looks like. And if I add these two together, then I get the result onto the stack. So this is a nice, simple tool to play around with these opcodes. And for those interested, I'm going to post a set of 2 little exercises. And based on the knowledge that you see that you've gained from this talk, I'm also going to post these slides. You should be able to write these tiny little contracts. First, you'll write a contract that reverts if your call data is empty. Else return 3. So one thing you're going to want to look at is this website here. Any opcode that you want to use or search for is going to be here. So for call data, there is some call data opcodes here. Call data size will tell you the length of it. Call data load will load data from call data, and so on. And down here, we also have a second one, which is to take whatever is in storage slot 7 and return the sum of that plus the ether received. So seeing this storage slot 7, this is going to involve an sload. Sum is going to involve an add opcode. Ether received is going to involve the call value opcode because you're receiving ether from the sender.